Imagine, just for a second, a computer so advanced, so mind-bendingly powerful, that it could look at a problem that would take the fastest supercomputers we have right now, the ones that fill entire rooms and cost hundreds of millions, a billion years, and solve it in minutes. This isn't just a futuristic fantasy anymore. Back in 2019, Google dropped a bombshell with their quantum computer, Sycamore. It performed a calculation in a mere 200 seconds, a task they estimated would take a top-tier classical supercomputer, wait for it, 10,000 years. Now, fast forward to today. Just recently, Google revealed their latest quantum marvel, the Willow chip. And the leap is even more staggering. A calculation that Willow can complete in under 5 minutes. The time it might take you to grab a coffee would take a classical supercomputer. Hold on to your hats. 10 septillion years. That's a 10 followed by 25 zeros. It's a number so big, it practically loses meaning. It's longer than the age of the universe by a factor of 1,000,000 trillion. But here's the part that truly blows the doors off our perception of reality. Willow isn't just brute force faster. It's rumored, it's speculated, it's even suggested by some of the brilliant minds building these machines that this incredible power comes from something else, that these computers aren't just working in our universe, that they're somehow tapping into the very fabric of existence, computing across parallel realities. What if the secret sauce, the key to this almost supernatural computational ability, isn't found solely within the circuits and qubits of this machine in a lab, but lies in a vast, unseen multiverse, where every single possibility you could imagine plays out? That's the story we're unraveling today. We're about to dive into the quantum realm, explore mind-bending theories, and grapple with ideas that might just change how you think about yourself, your choices, and reality itself. So seriously, buckle up. This is going to be a wild ride. Let's start by grounding ourselves just a little before we launch into the cosmic. We need to understand why quantum computers are such a monumental leap, something fundamentally different from the machines we use every day. Think about the history of computation. We humans have always been problem solvers, and we've always used tools to extend our abilities. From using our fingers to count sheep or stones, to creating abacuses for more complex tallying, we've built systems to process information. That journey led us, eventually, to the classical computers we all know and rely on. Your laptop, your phone, the servers that run the internet, they all operate on the same fundamental principle: bits. Information is stored as either a 0 or a 1. Solving a problem on a classical computer is like navigating a maze. The computer tries one path. If it hits a dead end, it backtracks and tries another. It's incredibly fast at this, trying billions or trillions of paths per second. But it's ultimately sequential. It follows one logical route at a time, even if it jumps between them very quickly. It's methodical, deterministic, and bound by the rules of our everyday, classical world, where things are either here or there, on or off, 1 or 0. Like a car, driving down a single road. Now bring in the quantum computer. Instead of classical bits, they use qubits. And this is where things get weird, wonderful, and powerful. Thanks to the bizarre rules of the quantum realm, a qubit doesn't have to be just a 0 or a 1. It can be both simultaneously, thanks to a phenomenon called superposition. Imagine that maze again. A classical computer is trying one path at a time. A quantum computer, because its qubits can be in multiple states at once, can explore many paths simultaneously. Think of it not as a single car, but as a cosmic fog, or maybe millions of cars, instantly exploring every possible turn in the maze, all at once. If one path leads to a dead end, that version of the computation simply ceases to be the successful one, while other versions, exploring other paths, continue unimpeded. It doesn't need to backtrack in the traditional sense. The possibilities are explored in parallel. This ability to explore multiple possibilities simultaneously is the source of quantum computers' exponential power for certain types of problems. It's not just a little faster, it's a fundamentally different way of computing. For benchmarks like random circuit sampling, which Google used to demonstrate Sycamore and Willow's capabilities, this parallel exploration is what allows them to far outstrip classical machines. It's like comparing someone walking a marathon to someone teleporting across the finish line. In practical terms, this isn't just an abstract speed-up. This capability could revolutionize entire fields. Take cryptography. Much of our modern digital security relies on the fact that factoring very large numbers is incredibly difficult and time-consuming for classical computers. It would take billions of years. But a quantum computer, using an algorithm developed by Peter Shor, could factor those same numbers in seconds or minutes. This could potentially break most of the encryption used today. On the flip side, quantum computers could also create new forms of unbreakable encryption. But, as we hinted at the beginning, there's a school of thought, championed by physicists like the visionary David Deutsch, one of the pioneers of quantum computing theory, that suggests this mind-bending power isn't just about clever engineering and exploiting superposition within our single universe. They propose that quantum computers, when their qubits are in superposition, are actually performing calculations across parallel universes. Think about that. Every qubit, existing in multiple states at once, might not just be some abstract probabilistic state in our universe. It might represent different versions of the computation happening simultaneously in countless parallel realities. If this view is correct, then every time Google's Willow chip hums with activity, it's not just crunching numbers in a lab in California. It's engaging in a form of cosmic collaboration, receiving input and contributing to calculations happening in universes we might otherwise never know existed. Can you truly wrap your head around a machine that doesn't just solve problems, but dances across dimensions to find the answer? To really grasp this incredible idea that quantum computers might be tapping into parallel worlds, we need to take a necessary detour into the strange and beautiful world of quantum mechanics. This is the science of the very, very small, the rules that govern atoms, electrons, and photons. And let me tell you, those rules are nothing like what we experience in our everyday lives. Classical physics, the physics of Isaac Newton, works perfectly for describing how apples fall from trees, how planets orbit the sun, or how a baseball flies through the air. It describes a world that feels predictable, where things are where they are and follow clear paths. But try to apply those rules to an electron, and they completely break down. At the quantum level, particles don't behave like tiny billiard balls. They are fuzzy, probabilistic, and maddeningly unpredictable in ways that defy our intuition. They can, as we discussed, exist in multiple places or states at once. This is where quantum mechanics steps in, providing a mathematical framework to describe a reality that is fundamentally different from the one we see around us. Perhaps the most famous or infamous illustration of this weirdness is Schrödinger's cat. It's a thought experiment. Thankfully, no actual cats were harmed or put in boxes by Erwin Schrödinger. Imagine a sealed box containing a cat, a small amount of radioactive material, a Geiger counter designed to detect radiation, a hammer, and a vial of poison. The setup is rigged so that if the radioactive material decays, a quantum event, the Geiger counter detects it, which triggers the hammer, which breaks the vial, releasing the poison and killing the cat. Now, the decay of a radioactive atom is a quantum event. Until you observe it, the atom exists in a superposition. It is both decayed and intact simultaneously. And because the cat's fate is linked to the atom's state according to the standard rules of quantum mechanics, until you open that box and look inside, the cat is, well, it's both alive and dead at the same time. This isn't just a cruel philosophical puzzle designed to confuse students. It highlights a fundamental aspect of the quantum world. Systems can exist in a superposition of all possible states until they are measured or observed. It's like flipping a coin that spins forever in the air, simultaneously heads and tails, until the moment it lands and you look at it. Only then does it settle into one definitive state. But what exactly does measured or observed mean? And what happens to those other potential states? This is where the debate gets intense and leads us directly to the idea of the multiverse. The most traditional view, the Copenhagen interpretation, suggests that the act of measurement somehow collapses the quantum system's superposition into a single, definite reality. Before observation, the coin is heads and tails. After you look, it becomes one or the other. The other possibilities simply cease to exist in our reality. However, the many worlds interpretation, MWI, first proposed by Hugh Everett III and championed today by many, including David Deutsch and physicist Sean Carroll, offers a different, perhaps even more mind-bending explanation. According to MWI, when a quantum event occurs and a system is measured, the universe doesn't just collapse into one outcome. Instead, every possible outcome actually happens. The universe effectively splits, or branches, into separate, parallel universes, one for each possible result. So going back to Schrödinger's cat, when you open the box, according to MWI, you aren't collapsing the cat's superposition. You are simply experiencing one branch of reality where the atom decayed and the cat is dead, while a parallel version of you, in a parallel universe that just branched off, is experiencing the outcome where the atom didn't decay and the cat is alive and well. Think about the implications of this for your own life. Every decision you've ever made, every tiny quantum fluctuation in your brain that might have tipped the scales one way or another, every interaction with the world, it could have spawned a new branch of the universe where you chose differently. The time you decided to take that job offer instead of the other, the moment you turned left instead of right, even what you decided to eat for breakfast this morning. According to MWI, there are other universes where you made the opposite choice, and a version of you is living out that alternative reality. It's an incredibly difficult concept to accept because it flies in the face of our single reality experience. But proponents argue it's the most straightforward interpretation of the mathematics of quantum mechanics, specifically Schrödinger's equation, which describes the evolution of a quantum system over time as a wave of probabilities spread across all possible states. MWI suggests that this wave of probabilities isn't describing potential realities that might happen in the future, but rather describing the coexisting states across a landscape of actual parallel universes. So, are you just one thread, one particular sequence of choices and quantum events in a vast cosmic tapestry woven from countless parallel realities? If the many worlds interpretation is correct, the answer is a resounding yes. If the idea of universes splitting with every quantum event feels too abstract, let's look at one of the most famous, most beautiful, and most baffling experiments in all of physics: the double-slit experiment. It's often described as the heart of quantum mechanics, and some argue it provides the most compelling, albeit indirect evidence, for the many worlds interpretation. Here's how it works in its simplest form. Imagine you have a device that shoots tiny particles like photons, packets of light, or electrons, one at a time. You fire them towards a barrier that has two narrow slits cut into it. Behind the barrier, you have a screen that detects where the particles land. Now, if these were just classical particles, like tiny marbles, what would you expect to see on the screen? You'd expect them to go through one slit or the other, creating two distinct lines of impacts on the screen, directly behind the slits. Simple, right? But that's not what happens when you fire quantum particles, even one at a time. Instead of two lines, you see an interference pattern. a series of bright and dark bands on the screen. This pattern is characteristic of waves. Think of dropping two pebbles into a pond. The ripples spread out and interfere with each other, creating areas where the waves reinforce, bright spots, and areas where they cancel each other out, dark spots. This experiment suggests that individual quantum particles, like photons or electrons, behave like waves, somehow passing through both slits simultaneously and interfering with themselves. This is already mind-bending enough. How can a single particle go through two places at once and interfere with itself? But David Deutsch points to a fascinating variation of this experiment that he believes strongly supports the many worlds view. What happens if you add more slits to the barrier? Let's say you add two more, so you have 4 slits. You might intuitively think that adding more paths would just make the interference pattern brighter, or maybe a bit blurrier, as the waves spread out and interfere in more complex ways. But something utterly unexpected happens. If you look at a specific spot on the screen, a spot that was bright when you had only 2 slits open, that same spot can actually go dark when you open the additional 2 slits. Think about that. Adding more options, more ways for the particle to get to the screen, can actually reduce the probability of it arriving at a certain spot. How can this be? Deutsch argues that this is impossible to explain if only one photon is traveling through our universe. He suggests that the interference pattern, especially the disappearance of the bright spot when more slits are opened, is caused by our photon interacting with its counterparts, shadow photons, traveling through the other slits in parallel universes. In his view, when a photon approaches the 4-slit barrier, the universe splits. In one universe, the photon goes through slit 1, but in parallel universes, identical photons go through slits 2, 3, and 4. These shadow photons, traveling in these other realities, are still quantum mechanically linked to our photon. Their presence, their alternate paths in parallel universes, subtly influences the probability of where our photon lands on the screen in our universe through quantum interference. The destructive interference from the paths taken in other universes causes the bright spot in our universe to go dark. This perspective paints a picture where our reality isn't isolated. Every quantum event, every particle's journey, could be subtly influenced by its counterparts in parallel universes. We don't see these other universes directly, but we feel their presence through this interference pattern. And this interference? This is the very mechanism that quantum computers exploit. By maintaining qubits in superposition, allowing them to exist in multiple states simultaneously, these machines are essentially setting up a situation where calculations are performed in parallel across different branches or possibilities. The interference between these parallel computations is then carefully measured and directed to yield the desired result in our universe. When we marvel at the speed of a quantum computer, we might literally be witnessing the echoes of calculations performed in realities we can't perceive, their influence funneled into a useful answer in our own. It's as if these machines are designed to listen to the whispers of the multiverse. Okay, so if everything at the fundamental level is quantum, if particles can be in multiple places at once and potentially interact with counterparts in parallel universes, then why don't we see this weirdness in our everyday lives? Why isn't your coffee mug in superposition, both on the table and floating in the air? Why aren't you in 2 places at once? The answer lies in a crucial concept called quantum decoherence. Imagine that perfectly tuned symphony I mentioned earlier, representing a delicate quantum state like superposition. Decoherence is what happens when that symphony interacts with its environment. The air, the light, random vibrations, everything. A quantum system is incredibly fragile. When it interacts with other particles in its surroundings, its unique quantum properties, like superposition and the ability to interfere with itself or its parallel counterparts, get leaked or spread out into the environment. This entanglement with countless surrounding particles causes the system to rapidly lose its quantum coherence and start behaving classically. It's like the symphony musicians bumping into each other, dropping their instruments, and dissolving into chaotic noise. The beautiful, coordinated superposition is lost. This is precisely why macroscopic objects, anything large enough for us to see and interact with normally, like a coffee mug, a car, or you, don't exhibit quantum behavior. You're made of trillions upon trillions of atoms. Those atoms are constantly interacting with the air molecules bouncing off them, the light particles hitting them, the surface they're resting on, and the thermal vibrations within themselves. These interactions happen at an unimaginably fast rate. By the time even a tiny fraction of these interactions occur, any potential quantum superposition that the individual atoms might have had on their own is instantly smeared out, entangled with the environment, and lost. The system rapidly decoheres, settling into a single, definite, classical state. Your coffee mug is simply on the table. You are simply sitting where you are. Our everyday experience feels predictable and solid because everything around us is constantly decohering. But here's the crucial part. Quantum computers work precisely because engineers have become incredibly skilled at fighting decoherence. They isolate the qubits in extreme environments, often in super cold refrigerators just a fraction of a degree above absolute zero, shielded from electromagnetic noise and vibrations. By minimizing interactions with the environment, they can keep the qubits in their fragile superposition states for long enough to perform calculations. This mastery over decoherence is one of the biggest technical hurdles in building quantum computers, and succeeding at it is what allows devices like Google's Willow chip to even function. In essence, our everyday world feels classical because it's incredibly noisy from a quantum perspective. Decoherence is constantly collapsing all the potential quantum weirdness into a single, observable reality. But it raises a profound question. If we are fundamentally made of quantum particles, is our classical experience of reality only showing us part of the picture? Could truly mastering the control of quantum effects, extending that control beyond shielded lab environments, unlock technologies that seem impossible today? Technologies that exploit superposition and interference in ways that could reshape everything from computing to materials science. And yes, perhaps even tap into capabilities that hint at a reality far vaster than our own. Let's circle back to the raw power of these machines and the tantalizing possibility that it stems from the multiverse. We talked about bits and qubits. Classical computers store information in bits, either 0 or 1. With n bits, you can represent n pieces of information, each being either 0 or 1. A quantum computer uses qubits, which can be in superposition. With just one qubit, you can represent 0, 1, or a superposition of both. With 2 qubits, you can represent 0, 0, 0, 1, 10, 11, or a superposition of all 4 possibilities simultaneously. Add a third qubit, and you can represent all 8 possible 3-bit numbers at once in superposition. The number of states a quantum system can represent simultaneously grows exponentially with the number of qubits. 2n. Think about that scale. A quantum computer with just 50 qubits can represent 2050 states simultaneously. That's over a quadrillion possibilities. To store that much classical information would require a petabyte of memory, a massive amount. But here's the truly mind-boggling part. Scale up to, say, 300 qubits, which is still relatively small for some future estimates, and the system can represent 2,300 states simultaneously. That number, 2,300 Lars, is larger than the estimated number of atoms in the entire observable universe. No classical supercomputer, no matter how large or fast it is, can possibly hold or process that many states at once. They are fundamentally limited by the classical nature of bits and sequential processing. This exponential capacity is precisely why quantum computers are expected to excel at certain problems that are currently intractable for classical computers. We already mentioned Shor's algorithm for factoring large numbers, a cornerstone of modern encryption. There are also algorithms for search, Grover's algorithm, optimization problems, finding the best solution among a vast number of possibilities, like logistics or financial modeling, and perhaps most excitingly, simulating quantum systems themselves, like molecules for drug discovery or new materials, something classical computers struggle with immensely. For example, simulating the behavior of even a relatively small molecule can require computational resources far beyond what's currently available classically. But a quantum computer might handle it with relative ease. But where does this incredible speed and power come from? This is where David Deutsch's view takes center stage. He argues that the exponential speedup isn't just about manipulating abstract probability states within our universe. It's because the computer is literally performing calculations in parallel across a multitude of universes made available by the qubit's superposition. Each qubit in superposition isn't just probabilistically a 0 and a 1 in our reality. According to this interpretation, it represents distinct states existing in different branches of the multiverse. The quantum computer sets up a problem in this state of superposition, and then calculations proceed simultaneously in countless parallel universes. The resulting quantum interference between these parallel computations is then measured in our universe, and it is this interference that provides the correct super-fast answer. When Google's Willow chip solves a problem in under 5 minutes, that would take a supercomputer 10 septillion years. According to this perspective, it's not just a faster machine. It's a machine operating on a cosmic scale, leveraging computational resources spread across an unimaginable number of parallel realities. It's not just computing faster, it's computing differently by listening to the collective outcomes from across the multiverse. Could this truly mean that our future technological breakthroughs, the solutions to some of the world's hardest problems in medicine, energy, or climate science, will rely on machines that are, in essence, harnessing the computational power of realities we can't even physically touch? The prospect is mind-boggling. The implications of the many worlds interpretation and the idea of a multiverse don't stop at physics or computing. They plunge headfirst into some of the deepest philosophical questions humans have pondered for millennia. If every possible outcome of a quantum event, and our universe is filled with them, from the decay of a single atom to the firing of neurons in our brains, actually happens in a parallel universe, what does that mean for concepts like free will? In one universe, you decided to read this story all the way through. In another, maybe you got bored and clicked away 5 minutes ago. In yet another, you never even saw the title. If every single possible choice or outcome is realized somewhere in this vast, branching cosmic tree, does the idea of you making a free choice in this particular universe still hold meaning? If all paths are taken somewhere, are you truly choosing or simply following one predetermined path in a larger landscape where all paths are predetermined to be taken? Some philosophers argue that free will exists and is meaningful within each individual universe. From the perspective of the you in this universe, your choices feel real. They have consequences that you experience, and you are making decisions based on your desires, beliefs, and circumstances within this specific reality. The existence of other yous in parallel universes, they would argue, doesn't negate the feeling or reality of choosing within your own stream of events. Others might contend that the multiverse makes the concept of free will, as we typically understand it, irrelevant. If every outcome happens regardless of your conscious feeling of choice, then perhaps the feeling of choosing is an illusion, or simply the way the universe unfolding feels from our limited perspective within a single branch. Then there's the question of identity. If there are countless versions of you in parallel universes, each making different choices, experiencing different lives, are they really you, or are they separate individuals? Sean Carroll, a prominent physicist and proponent of MWI, uses the analogy of a cell splitting. When a single cell divides, you get two new, distinct cells. They started from the same origin. They might be identical for a brief moment, but they immediately begin to evolve separately, interacting with their distinct environments, experiencing different things, and diverging over time. The you who didn't read this story is like that other cell, perhaps starting from the same point, but quickly becoming a different person shaped by different experiences. In practical terms, grappling with these ideas might not immediately change how you live your daily life. You still wake up in this universe, face the challenges and opportunities here, and your actions have consequences in this reality. But the idea can certainly invite deep reflection. If every version of you exists somewhere, what makes the choices you make right here, right now, meaningful? Perhaps their meaning comes not from being the only possible choice, but from the fact that this is the reality you are experiencing. The one where your specific sequence of choices writes your unique story. Maybe the practical lesson here is about perspective. You can't jump to another universe where you made a different choice. But knowing that other paths could have been taken, or are being taken by other versions of you, can perhaps free you from regret about past decisions, or inspire you to pursue a path you might have been afraid to take, knowing that a version of you is already succeeding at it somewhere. It could encourage a mindset of possibility and resilience. This conversation inevitably leads to the question that pop culture loves to explore. Can we travel to these parallel universes? Could you step through a portal and meet another version of yourself? Could you revisit a past decision point in another reality and try to change things? Based on the current scientific understanding of the many worlds interpretation, the answer from physicists like Deutsch and Carroll is a pretty firm no. Parallel universes, in this view, are not just out there, like distant galaxies. They are branches of reality that diverge from quantum events. They don't exist in a space that you can navigate with a spaceship or a dimension-hopping machine. The only known connection or interaction between these branches is through that subtle quantum interference we discussed, like the effect seen in the double-slit experiment. There is no known physical mechanism for a macroscopic object, like a human being, to jump from one universe branch to another. Even if there were, as we discussed regarding identity, the you in that other universe has already evolved based on their own history of quantum events and choices. They are not simply waiting for you to show up. They are living their own, distinct life. Any attempt to interact would likely just cause further branching, creating yet more universes. So, while the idea of multiverse travel makes for fantastic movies and books, the scientific picture suggests a reality where the parallel worlds are intimately connected at the quantum level, but fundamentally separate at the macroscopic level we inhabit. However, and this is a big however, even if we can't visit the multiverse might already be here, influencing our reality in profound ways, particularly through technology. As we've explored, if David Deutsch and others are right, quantum computers like Google's Willow chip are, in a sense, touching the multiverse. They may be harnessing the interference effects from calculations happening in parallel realities to perform tasks that are impossible for classical machines. This isn't about stepping through a portal, but about leveraging the very structure of reality at its deepest level. Think about the potential applications we mentioned. Solving complex optimization problems that could make global supply chains incredibly efficient, simulating molecular interactions to design life-saving drugs in a fraction of the time, developing AI algorithms with capabilities we can't currently imagine, or modeling climate systems with unprecedented accuracy to find solutions. These practical breakthroughs, powered by quantum computation, could fundamentally reshape our lives, indirectly delivering the benefits of tapping into a vaster computational landscape. So while we might never physically travel to another universe, the lesson here isn't one of disappointment, it's one of empowerment. We are firmly rooted in this reality, in this branch of the cosmic tree. And within this reality, we have agency. We can make choices that align with the future we want to see. The multiverse idea, far from making our reality insignificant, highlights that this specific sequence of events, this particular journey, is the one we are living. And that makes the choices we make here incredibly precious and powerful. So what can we truly take away from this mind-bending journey through quantum mechanics, parallel universes, and the incredible power of quantum computing? First and foremost, it's a powerful reminder that reality, the universe we inhabit, is far stranger, more complex, and more wondrous than our everyday intuition often allows us to believe. The same fundamental physics that describes the fuzzy, unpredictable behavior of a single electron also suggests that our universe might be just one of many, each playing out a different variation of the cosmic story. This perspective can be incredibly humbling, reminding us how much we still have to learn, but also incredibly inspiring, fueling our curiosity to keep exploring the deepest mysteries of existence. On a personal level, the idea of the multiverse, perhaps paradoxically, can ground us and encourage us to focus on the reality we are actually experiencing. You can't change the past. You can't jump to another universe where you made a different decision or where things turned out differently. But you can shape the future of this reality, your branch of the cosmic tree, with the choices you make right now. Whether it's pursuing a long-held passion, mending a broken relationship, facing a difficult challenge head-on, or simply choosing kindness in a small interaction, your actions have tangible consequences in this universe. Embrace that power. Let the knowledge that infinite possibilities might exist elsewhere motivate you to make the most of the possibilities that are available to you right here. It's about consciously choosing the path you want to walk in this specific reality and pouring your energy into making it meaningful. Finally, this exploration teaches us the profound value of staying open-minded and curious. Concepts like quantum, superposition, and entanglement once seemed like abstract, almost philosophical ideas confined to the realm of theoretical physics. Yet, they are now the foundational principles driving technologies like quantum computing that have the potential to transform industries and solve problems that affect billions of lives. What other seemingly impossible ideas, whether in science, technology, or even our understanding of consciousness, might be waiting to move from the realm of speculation to practical reality? Keep asking questions, keep exploring, keep learning, because the universe, or perhaps the multiverse, is full of surprises, and the next big breakthrough might come from the most unexpected place. Does the idea of parallel universes excite your imagination? Does it feel unsettling, or does it just raise a mountain of questions? If you could, for just a moment, glimpse another version of yourself in a parallel universe, what choice would you hope they made differently? Or perhaps, what choice would you hope they made the same, confirming that some things are fundamental across realities? Share your thoughts in the comments below. I read every one, and I'm genuinely curious to hear how this story resonates with you. And if the deep dive into quantum mechanics or computing has sparked your curiosity, I highly recommend checking out resources like brilliant.org. They have incredible interactive courses that make these complex concepts come alive, and are a fantastic way to continue exploring. Not sponsored, just a great resource. If you enjoyed this exploration and want to join us for more journeys that challenge how we see the world, hit that subscribe button and ring the notification bell. Let's keep exploring the universe, or maybe even the multiverse, together.